Assalamualaikum and good afternoon. So today we are from Group 3. We are going to present our Fourier series analysis project. So this is our group member, Muhammad Hafizuddin bin Razali, Muhammad Zikri Zubair bin Rudi, Muhammad Azwan bin Rosli, and me, Muhammad Fikri bin Rahimi, and Logan anak lelaki Karunaniti. So let's continue with our methodology. Okay, so I'm going to present our methodology for this project. This project analyzed a 30 kHz square wave, which is 50% duty cycle using Fourier series. The signal is reconstructed with 5, 10, and 20 harmonic, showing improved accuracy with more terms. Since square wave contains only odd harmonic, cosine terms, and odd multiple of the fundamental frequency are summed using calculated Fourier coefficient. Then, the signal frequency content is visualized using a sample of the harmonic amplitude. A first-order RC low-pass filter with a cutoff frequency of 520 kHz is then applied to simulate a real-world signal processing. The filter attenuates high-frequency harmonic, and the filter signal is reconstructed to observe its smoother shape in the time domain.
My name is Rogan Alaki Karunanidhi and my matrix number is CE220103, and as part of methodology I will show you the coding we use. Is the coding we use in this project, and the F4 equals to 30E3 refers to the fundamental frequency equals to 30 kilohertz, and the T0 equals to 1 slash FO refers to the period of square wave, and the tau equals to 0.5 star TO is referred to 50% duty cycle, which is symmetric square wave, and the T refers to a time vector for simulation, and the N values equals to 5, 10, 20 is the number of harmonic used for approximation. For the main loop, for each N, construct the signal using only odd harmonics 1, 3, 5, and dot dot 2 N minus 1. Compute each harmonic coefficient is we use as Cn. The accumulate sum of cosine to the former approximate signal is xt, and the x-axis we plot in is time in microsecond, and y-axis is amplitude. For part 2, which is frequency domain analysis, the harmonic setup is n equals to 20 harmonics, and n harmonics equals to 1 ratio 2 is referred to odd harmonics, first, third, fifth, and so on. The frequency equals to n harmonics star FO. FO refers to frequency for each harmonics, and the Cn is Fourier coefficient for each harmonic. Cn equals to 2 over pi n dot sine n pi tau over TO represent the amplitude of each harmonic component, and the x-axis is frequency in kilohertz, y-axis is the magnitude of coefficient. For part 3, which is low pass filter frequency response, f equal to lin space 0 1 e 6000 is referred to the frequency vector from 0 to 1 megahertz. Fc equals to 520 E3 is the cutoff frequency which is 520 kilohertz. The HF equals to 1 equals to the first order low pass filter formula. And for the part 4, which is apply filter in frequency domain, Hn equals to the filter gain at harmonic frequencies. The Cn filter equals to Cn star Hn is the applies filter gain to each Fourier coefficient, and Cn star HF is the filtered magnetic spectrum to show the harmonic attenuated. And the part 5 is reconstruct filter signal time domain. The square wave equation is xt equals to sum of Cn dot cos 2 pi n f4t. The Cn filtered underscore filter is used to form smooth version of signal square.
Okay, Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad Hazwan Berosi with the matrix numbers of DE220087. Okay, so I'll be presenting for the result part for the part 1, part 2, and part 3. Okay, so let's go with the first one. It's actually for the time domain reconstruction using Fourier series. This is to actually show that we have successfully reconstruct the signal by using 5, 10, and 20 harmonics. Okay, so the result showed with only 5 harmonic, the waveform roughly resemble a square wave, but has a feature the rounded transition. It lacked the edge characteristic for ideal square wave. And then we using the 10 harmonics that show much clearer. The high and low level were more stable, and the rising and falling edge is steeper. However, there are still some ripples, something like that, on the upper part and the lower part transition. And then after we increase it to 20 harmonics, the square wave has closely approached the ideal shape. The transition were better, steeper, and the flat region has more stable, but the ripples still remain visible near the edge. Okay, so that's for the part 1. While for part 2, the magnetic spectrum actually show the original square wave that is plotted by using the first 20 odd harmonics. The plot actually show strong peaks at odd multiple of base frequency for 30 kHz, 90 kHz, 100 and 150 kHz. These peaks gradually decrease in amplitude as the harmonic number increase. This actually follow the formula of 1 over n decay time. The result actually matched the theoretical expectation for a 50% duty cycle square wave where even harmonic are absent. Okay, so that's for the second part. And the last one, that is part 3 for me, that is low pass filter frequency response. The frequency response of the design low pass filter has cut off at 520 kHz show that the classic behavior of a first order filter. It has good flat gain of near 0 dB for frequencies below the cutoff, and then it gradually became flat signal beyond that point. The gain dropped to negative 3 dB exactly at 520 kHz, confirming the accuracy of the design. This filter actually implied that harmonic component below 520 kHz would pass mostly unaffected, while those above actually probably would be increasingly suppressed. That's all for me.
Hello, my name is Mohammad Zikri Zubair bin Rudi. So I will be presenting figure 4 and 5. So as you can see here, we have the filtered magnitude spectrum, which shows the result of applying a low-pass filter to the Fourier series component of square waves. So we can see here the x-axis represents the frequency in kilohertz, and the y-axis shows the magnitude of each harmonic component after filtering. And as you can see here, the first few harmonics are preserved with relatively higher magnitude, which particularly the fundamental frequency at 30 kilohertz. So as the frequency increase beyond the filter's cutoff frequency, set uh, set at 520 kilohertz, and the magnitudes starts to drop sharply. This is clearly demonstrates the behavior of the RC low pass filter, which allows the low frequency components to pass while attenuating higher frequencies. So the result is a smoother time domain signal with reduced sharp transitions, which we can visually confirm in the waveform after filtering. So this plot highlights how filtering impacts the signal's frequency content and supports the core principle of frequency domain signal processing. And so for this last figure displays, which is a reconstructed square wave in the time domain after applying a low pass filter to its Fourier series components. So the signal retains the basic square wave shape, but the sharp transitions are visibly smoother, which this occurs because the higher frequency harmonics, which contribute to the sharp edges, which have been attenuated attenuated by the filter. The low pass filter with a cutoff frequency of 520 kilohertz allows the lower frequency harmonics to pass while reducing the contribution of higher ones. So as a result, the waveform becomes more rounded and less ideal, illustrating the relationship between frequency content and time domain signal characteristics. Uh, this, which is clearly demonstrates an important concept in signal and systems, um, how of how modifying the frequency components of a signal affects its time domain representation. And that's all from us for the result and analysis, and will be continued for the last one.
So, in conclusion, this project demonstrated Fourier series analysis of a 30 kHz square wave and the effect of adding 5, 10, and 20 harmonics for signal reconstruction. As more harmonics were included, the waveform better resembled an ideal square wave, illustrating the Gibbs phenomenon. Frequency domain analysis confirmed the presence of only odd harmonics. A low-pass RC filter with 520 kHz cutoff was applied to show how high-frequency components are attenuated, smoothing the signal in the time domain. The use of MATLAB simulation and frequency domain filtering highlighted key signal processing concepts and reinforced both theoretical and practical understanding. That's all from us. Thank you.